Hey folks, last time we started talking about the Ford-Fulkerson algorithm. What I'd like to do today is go through a few more examples. Before we do that, I want to make an announcement about exam two. This exam two will be on March 27th. So that is 2 weeks and a day, 15 days from now. So that's, plenty of advance notice, I'm hoping. This is Saturday so that we could do what we did on the first exam and open the exam up for a window of time so that people can schedule the exam during the day for a convenient time rather than trying to squeeze it into a weekday. But if you have an objection to testing on Saturday and want to test on Friday or Sunday instead, get in touch with me soon so that I can start working on those arrangements, okay? Let's go ahead and get started. So, first of all, I want to just give some credit here because I am using somebody else's examples here. These examples came from the Alan Tucker Combinatorics textbook. These are because our textbook doesn't have a Ford-Fulkerson algorithm in it. So our goal here is to maximize the flow from the source, which is over here, to the sink. And the way we begin is we just go ahead and initially set the flow at every edge to 0. So we're not currently sending any data or goods or merchandise or whatever whatever this network is modeling. We're not sending anything yet. And then we look for a path from the source to the sink that has a non-zero bottleneck capacity. That's all we're just going to do. So we might try the path that goes along the top. So that would be from A to B to E to Z. All right. So in my first attempt, we're going to look at sorry about that, A, B, E, Z. And the bottleneck right here is 5 units here. I can add 10 units from A to B, but I can only add 5 units from B to E, and I can add 10 units from E to Z. Since I can only add 5 units across the whole path, that's my bottleneck capacity. I'm going to add 5 units here. I'm going to add 5 units here. That makes this edge full. And then I'm going to add 5 units down here. Okay. And then we try again. We look for another path. So we might try the path going down the bottom. And again, the bottleneck is this edge here in the middle that only has a capacity of 5. So that's ACFZ. And I can add 5 units there. So that's 5 units across here, 5 units across here, 5 units across here. And then we try again. So now we're going to have to do some kind of zigzaggy path. So how about from A up to B, down to F, up to Z. So what's my bottleneck now? From A up to B, I can only add 5 units. From B down to F, I can add 7, but I'm limited by this 5 over here. And then from F up to Z, I've got 10, but again, I'm still limited by this 5. And so A, B, F, Z is limited by just 5. And so I could add 5 units here. I could add 5 units here. And then I could add 5 units here. And that gets my flow up to 15. All right. So then we might try this path from A to C up to E down to Z. So just a mirror image of that path. And this time my bottleneck is going to be the 5 units limitation here from E to Z. This edge will allow 7. This edge will allow 10 more. But I can only fit 5 more here. So I'll add 5 units there. That takes my unit, this up to 10. This up to 5. By the way, this should have been a 5 also. I didn't see that before. This should have been a 5. And this should have been a 10. There you go. All right. So, and let's do that. I guess one other thing, since I didn't realize that there were 2 values here, as a value here and a value here, this is not an edge from B to F, it's an edge from B to D and then from D to F. And then this is an edge from C to D and then from D to E, not just a single edge. All right, now it's starting to get a little harder. So let's see what our options are. I could go from A to C. And then I could go up to B because I still have some capacity along here. And then I could get 2 more units down this diagonal here. That's at 5 out of 7. And I have enough capacity to get those 2 units there. So let's try this. If we go from A to C, up to B, down to D, down to F, then over to Z, I can get 2 more units there. That's going to take this edge here up to 12. There you go. Then up this edge is going to go from 0 up to 2. Come on. 2 out of 10. Then this edge will go to 7 out of 7. 7 out of 7. And then 12 out of 15. Okay. Is there anything else we could do? I can add 3 more units down here. I could send 2 of those units up this diagonal this time. Down here, I've got a lot of capacity on this edge. This is still at 0 out of 10. And then I could get 2 more units going along here. But my bottleneck is going to be along this edge from C to D and from D to E. All right. So let's look at that. That goes from A to C to D to E to F to Z. We're going to add 2 more units. This is going to take me up to 14. All right. That fills this up. This fills this up. This is going to go to 2 out of 10. And this is going to go up to 14 out of 15. All right. So, can we squeeze 1 more unit out? There's still room for 1 more unit to come out of the source, going down this edge. But there's nowhere where it can go now. There is a theorem, and I'm not going to write out a formal statement of the theorem, but there's a theorem that says if you could draw a line anywhere through the graph, anywhere through the network, and have the flow be full at every line, every place across that line, then you are at your maximum capacity. That is, I can't get anything from the source to the sink because it would have to cross this line at some point. And it crosses it along this edge because it's full, this edge is full, this edge is full, and this edge is full. So I hope that reasoning makes sense. If there's a line that absolutely can't be crossed between the source and the sink, then you have to be at maximum capacity. And so the maximum capacity is the maximum flow, in this case, is 24 units. I do have one extra capacity here from A to C, but there's nowhere it can go. It could go up to here, but then it hits a dead end because it can't go out through any of those other edges. So we found all the different paths we could find that would allow us to increase the flow, and then once we ran out of paths, we stop. So that's the idea behind how Ford-Fulkerson works. So let's try another example. This is kind of a messy looking example, but it's not too bad. We're going to try the same sort of thing here. We're going to try to find paths that go from the source all the way to the sink and see what we can do with them. So I like to do the top and the bottom first, just if I'm doing this by hand. So let's try the top path. It's A, B, E, Z. And its capacity is 4. Let me go ahead and put 4 along each of these edges. That's my first attempt. And then if we go along the bottom, we can go from A to D to G to Z. And the bottleneck capacity is 4 here. So we can add 4 along the whole path. And we can go straight across the middle from A to C to F to Z. And that I can only add 2 because of these bottlenecks at the front and the end. All right. So this wasn't so bad to get started. Go across the top, go across the bottom, go across the middle. And now we're going to have to do a little bit more searching. I have more capacity from A to B. From A to C is full, and from A to D is full, but I do have more capacity from A to B. So where could those 4 units go? Well, 2 of them could go across, and 2 of them could go diagonally. And so let's see what would happen here. If they went diagonally, they couldn't come out this way from F to Z. They'd have to go further down from D, but then it looks like there's room to go ahead some of the rest of the way. So we found a path, A to B to E to C to G to Z. All right, let's try that one. The bottleneck is going to be 2 along this because from B to E I can only do 2. So that's going to take this edge up to 6. It's going to take this edge up to 6. It's going to take this edge to 2, this edge to 2, and then this edge up to 6. And then the other diagonal path is from A to B to F, down to D to G to Z. And we can add 2 along that path. That's going to take this up to 8. This will go down to 2. This will go to 2. This will go up to 6. That fills that up. And then this will go to 8. And I know I'm at maximum capacity because I can draw a line, and every edge along that line is full. This is at 8 out of 8. This is at 2 out of 2. This is at 4 out of 4. And so there's no way to cross that line getting from the source to the sink. And so if I can separate the source and the sink with this line, and no edges along that line have any additional capacity, then we cannot cross that line. And so we reach maximum flow in this. A can't send anything else out. We're at 14 units. That's our maximum flow. And we had to use every single edge in the diagram. We're not using all of them to capacity. There's some extra capacity here. There's some extra capacity here. We're wasting some capacity, but we're using every single edge. All right. We've done 2 more examples of walking through the Ford-Fulkerson theorem and looking for edges that allow us to add to the flow. I want to talk about how we might try to do this in a systematic way without just sort of looking for edges. How might we do this as a coding problem? And so some of you have done the idea before of navigating through a tree using what y'all call pre-ordering. We're in a tree. You would start at the root and then investigate the left node first and then the right node second. And then from the right node, you would indicate the left node first and the right node second. Actually, the left node comes before this right node, and then finally come back up here, 7, and then 8, and then 9. You would look at the edges. If you could go left, you would do that first, but if you couldn't go left, then you would back up and check to the right. In a graph like this, left and right is not the best way to go because we have vertices that are, say, directly above each other, and we can have edges like in the last example that flow from left to right and edges that flow from right to left. So we're going to try pre-ordering again, but instead we're going to use the alphabet. Alphabetical order is our pre-ordering. So if we start at the source, there are 2 edges I can go to. I can go to B, I can go to C, and my pre-ordering is going to say we go to B first because it shows up earlier in the alphabet. And so what I'm going to do is I'm going to start doing that. I'm going to say if we go from A to B, because B shows up earlier in the alphabet, and look at the paths that we can get from there. From B, we can go to D or we can go to E, but D shows up earlier in the alphabet. And then from D, we can either go backwards to C or forwards to Z, but C shows up earlier in the alphabet. Then from C, we can go forwards to E. I'm not counting backwards to A because I've already listed A. I'm only looking at new vertices so that I don't create a cycle. A to B to D to C back to A is a cycle. So I can go forwards to E, and then I could go forwards to Z. If I'm doing pre-ordering, this would be the first path that I would check. So then, again, doing pre-ordering, let's see what would the next edge we could check. E can't go anywhere other than Z. If we back up to D, we had a choice between C and Z. So the other path would be to go from D to Z. Now, if we back up even further, B had a choice between going to D and going to E. So let's look at what had happened from E. E could go backwards to C or forwards to Z. Alphabetically, C comes first. And then C can reach the sync by going to D to Z. Or E can go straight to Z. And those are the two different directions we can go to from B. B can go to D or B can go to E. And we've looked at BD and BE now. So let's go down to C. A can go to C. C can go to D or E, but pre-ordering says we go to D first because we're using alphabetical ordering for our pre-ordering. D can go backwards to B or forwards to C. So if we do backwards to B first, we have to finish it with E to Z. Or we can go to Z directly. And if C, instead of going to D, it goes to E, E has the choice of going backwards to B or forwards to Z. We go backwards to B. The next choices are D and Z. And if we go directly to Z, that finishes us up. In other words, what I've just done here is I've used pre-ordering to come up with a list of all of the different paths that get me from the source to the sink that don't have cycles in them. Not having cycles is important in this because we don't want to have goods and data just traveling in a loop. We want to actually get to the sink. And so let's start scanning this list and looking for what we can do here. So if we go through this list first, remember we start out with a capacity of 0 on every edge. All right, and I look for bottleneck capacities. So I'm going to start trying the first path. From A to B, my capacity is 12. From B to D, my capacity is 10. From D to C, though, because I'm going backwards along the arrow, we're not adding, we're subtracting, and there's nothing to subtract here. My capacity is 0 along this edge. And so my bottleneck is going to be 0. So I cannot add anything along that path. So then let's try ABDZ, which is just straight across the top. A to B is 12, B to D is 10, D to Z is 5. So I could add 5 along this path. So I do that. So let's check this path. A, B, E, C, D, Z. So A to B, is 7 now, is my capacity. B to E is 4. E backwards to C, though, is 0, because when we go backwards, we subtract instead of add, and there's nothing to subtract here. So I can't do anything along that path. So we go A to B to E to Z. So my capacities are 7, 4, and 18. 4 is my bottleneck. So we can add 4 along this path. That takes me up to 9 and 4. and 4 here. All right. Okay, let's check this edge. A to C to D, back to B, up to E, over to Z. Well, the capacity is going to be, bottleneck is going to be 0, but I'm going to walk through this. A to C, I have a capacity of 10. C to D, I have a capacity of 8. So that takes me down to 8. D back to B, since I'm going backwards along this edge, I'm subtracting, but I can subtract 5. So I still have 5 units of capacity here. B to E, though, is going forwards, and this edge is full. I can't add anything from B to E to Z. So that's going to be 0. So let's look at A to C to D to Z. And again, this path is going to be full. A to C has a capacity of 10. C to D has a capacity of 8, but D to Z has the capacity of 0. So I can't add anything there. A to C to E, back to B, forward to D, and then on to Z is also going to be 0. A to C is 10. C to E is 12, but I'm still limited by 10. E going backwards to B is subtracting. That takes me down to 4. B to D, I can add 4 along here, but from D to Z is full, so I can't add anything along there. All right, so let's look at the bottom. A to C to E to Z. I can add 10 along this edge, 12 along this edge, 14 along this edge. I can add a whopping 10 units along ACEZ. That's going to take this up to 10. That's going to take this up to 10. That's going to take this up to 14. Okay? Are we good so far? All right. So are we at maximum capacity here? So let's look at what can happen now. A to C is full, so if I'm going to have any capacity at all, it's got to go from A to B. B to E is full, so if we would have to send it on to D. D to Z is full, and so we couldn't send it on to Z, but D to C is empty, and a backwards edge we're subtracting from, there's nothing to subtract from here. And so we reach a dead end at D. And so we can't add any more to the flow. We're stuck at a maximum of 19 units. We are underusing this network pretty seriously. This edge is completely empty. But this is our max flow. And pre-ordering gave me an entire list of paths that we could search. A lot of them had bottleneck capacities of 0. But if we wanted to be systematic about it, make sure we checked everything, this gives us a way of doing that. All right. I'm hoping these examples help make Ford Fulkerson a little clearer than just the one example that we did on Wednesday. If you still have questions, post them to the website or come by my office hours next week. We'll talk about this some more. Y'all have a fantastic weekend. Thanks for coming.